Hello everyone, welcome to my class. In today's class we start infinite series. So in our last class we studied infinite sequence. Now let me start the class right away. First, definition of a series. A series is an infinite sum of terms of a sequence. That is, if an is a sequence, then a1 plus a2 plus ... is called an infinite series, and we denote the infinite series by the summation of an equals to 1 to infinite, or simply summation an. So here this is a sigma notation, which means summation. For example, series n means 1 plus, put n equals to 1, put n equals to 2, and add them. So 1 plus 2 plus 3 plus ... Similarly, series 1 over 2 to the n means, again, put n equals to 1, put n equals to 2, put n equals to 3, and so on, and add this term, which means 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus ... Now, in this section, we wish to answer the following questions. What does it mean to add up infinitely many numbers? Does it even exist? So the idea is, the sum of the infinite series is defined as the limit of the sequence of its partial sum. So then, let's define the partial sums first. The nth partial sum, which is denoted by capital S n, of a series n is defined as capital S n equals to sum of the n many terms of the series. That is, S1 is, this is one term, S2 is the sum of two terms of a series, A1 plus A2, S3 is the sum of three terms of a series, so A1 plus A2 plus A3, and so forth. Then these partial sums form a sequence which is denoted by Sn, n1 to infinite, and limit of the Sn is the sum of our infinite series. Great. So at least we are making sense of an infinite sum as a limit of finite sum. Awesome. So next, let's talk about sum of a series. Sum of a series. An infinite series an, converges if the sequence of partial sums, the sequence of Sn, converges. More precisely, the sequence of partial sum converges means that the limit of Sn exists and the series converges, and the sum of the series turns out to be the limit of the sequence of partial sums. Great. Otherwise, we call the series divergent. Awesome. Quick example. Find the sum of the series 1 over 2 to the n using the sequence of partial sums. Great. So let me write the series in expanded form. So here my left side is a given series. On my right side, I put n equals to 1 the first term, n equals to the second term, n equals to 3 the third term, and so on. And let's define the partial sum here. So S1 is just the first term, S2 is the sum of first two terms, S3 is the sum of first three terms, and so on. That means we do have now sequence of partial sums. Sequence of partial sums, and limit of the Sn equals to limit of this 2 to the n minus 1 over 2n. Then using underlying function test, let's write this as a function, which is 2 to the x minus 1 over 2 to the x. Take the limit at x goes to infinite. Then using L'Hopital's, it turns out to be 1. Great. Hence, we found the sum of this infinite series 1 over 2 to the n is 1. So let me visualize here. So here's it's a total square here with a 1 unit length, 1 unit width. So we start from 1/2. This is 1/2, and then this is 1/4. This is 1/8. This is 1/16, 1/32, dot dot dot. So the sum turned out to be 1. Great. Let's move on. Quick remark. Changing a finite number of terms does not affect the convergence and divergence of a series. However, it may change the sum. For example, let's see for example 1. We found the summation of 1 over 2 to the n equals to 1. We start from n equals to 1. So if we start n equals to 0, that means we need to add the 1 over 2 to the 0 term. Means we need to add 1 over 2 to the 0 means 1. So then 1 plus, that's the, when you put n equals 0, that is 1 over 2 to the 0 is 1. So this is 1 plus this sum, 1 plus 1, 2. Great. Similarly, if I start from n equals 3 to infinite, then if I start from n equals to, then I need to subtract 1 minus the first term, n equals to 1 and n equals to 2, which I did here, which gives me 1/4. Awesome. Let's move on. There are two families of series whose sum is easy to find: geometric series, telescoping series. First, geometric series. A series of the form a plus ar plus ar square plus dot dot dot, whose sum is n equals to 1 to infinite, a times r to the power n minus 1, or simply summations arn, and runs from 0 to infinite. This series is called a geometric series, where r is the common ratio. Then sum of the geometric series. The geometric series converges for the absolute value of the common ratio is less than 1, and its sum equals to first term over 1 minus the common ratio. If the absolute value of common ratio is greater than or equals to 1, then the geometric series diverges. Quick example. The series 1 over 2 to the n is a geometric series with first terms 1/2, common ratio 1 over 2, which is less than 1. So the sum of this infinite series of 1 over 2 to the n equals to first term over 1 minus the common ratio. You simplify, it gives us 1, which we already computed earlier. Awesome. Next, telescoping series. A series whose partial sum is of the form Sn equals to, most of the term cancel out of that series, and it remains first terms and last terms, and sometimes some other term also. For example, find the sum of the series 1 over n times n plus 1. By the way, using partial fractions, we can rewrite 1 over n times n plus 1 equals to 1 over n minus 1 over n plus 1. It's not that hard to verify. You can take LCD, which is n times n plus 1. I'm talking on the right side here. So multiply n plus 1 here, multiply n here. That means you can cancel the n, so 1 left, 1 over n times n plus 1, which is my left hand side. Awesome. So it's quick solution here. So let's find the partial sum. So the partial sum Sn equals to, so summations 1 over k minus 1 over k plus 1. I wrote this is at the right hand side. I switched the index here, by the way. Then let's expand this on my right side. So put k equals to 1, k equals to 1. And then the second term is put k equals to 2, put k equals to 2, which is 3, and so on. And if you observe here, we can cancel this negative 1/2 and positive 1/2, negative 1/3, positive 1/3, and dot dot dot. Then 1 over n cancels here. That means what left? The first terms, and then the last terms are left. And take n goes to infinite. That means this fraction goes to 0. So we have only 1 left. So this implies the sum of this infinite series is 1. Awesome. Let's move on. Quick remark. In most sections now onwards, convergence divergence of a series will be our main focus of attention rather than to what number it actually converges to. Great. 2. Evaluating a series using the partial sum technique is a little messy. Instead, we analyze the term, nth term, an. Another alert: a sequence converge does not imply the corresponding series converge. For example, the sequence 1 over n is convergent and it converges to 0, but its sister series, the sum of an, which is sum of 1 over n, diverges. This is a harmonic series and in fact diverges to infinite. Quick visualization here. The sequence is here 1, 1 over 2, 1 over 3, dot dot dot, which is going to 0. But if we make a partial sums, then it going to infinity. Great. One quick fact: if the series an converges, then the limit of the nth term goes to 0. But the converse is not true. Let's move on. Quick observations. With every series, there are associated two sequences. One, the sequence of partial sums. One, the sequence of its terms. And if the series is convergent, then the limit of the sequence of partial sum equals to s. And in fact, this is the sum of the series, and limit of the nth term an is 0. Now, one very common and very useful test, whether the series convergent or divergent, which we call a divergent test, also called the zero test. It says if the limit of the nth term of the series is not equal to 0 or does not exist, then the series an is divergent. In other words, the shrinking test, the terms of the series must approach 0, else it diverges. So if a series does not pass the divergent test, then stop trying any other test for convergence, as it automatically series diverges. Great. Example 3. Find the sum of the series n over n plus 1. Let's use the zero test. So take the limit of the nth term. So limit of the nth term n over n plus 1. Then we factor the n out and cancel out. Then the limit as n goes to infinite gives us 1, which is not a 0. So by the zero test, the series diverges. Awesome. Let's move on. The properties of convergent series. If series an and series bn are two convergent series, then so are the following series. So the series of c times an convergent, series of an plus minus bn convergent, and we write the series c times an equals to, we can pull the constant outside, so c times the series an, and in series an plus minus bn equals to series an plus minus series bn. These are also convergent. Great. Now let's do examples. Example 4, so that the series 2 times 3 to the power n minus 1 over 5 to the n is convergent, and find its sum. Awesome. So let's begin the solutions. Here we can rewrite the given series as this way. So we can, in my denominator, we can factor the 5 outside, and then we put 5 to the power n minus 1, and I have n minus 1 power, so then I can write 3 over 5 power n minus 1. And it seems to me it's a geometric series, and we can pull 2/5 outside the summation notations. Then we have the series of 3 over 5 to the power n minus 1, and we know 3 over 5 is less than 1, so it converges, right? So here the geometric series, this is the geometric series, The first term is 2/5, put n equals to 1, so this term gives me 1. And common ratio is 3/5, which is less than 1, so it's a geometric series. Then its sum equals to first term over 1 minus the common ratio. So 2/5, 1 minus 3/5 becomes 5 minus is 2/5, and you flip it, 5/2 cancels, gives us 1. So we found the given series is convergent, and in fact it converges to this number 1. Great. Let's move on. Example 5. Determine whether the given series convergent or divergent. Let's begin solutions. Let's rewrite this given series. The sum is here. Let's distribute this sum. So that means we can write this as a sum of the series here. Series of the sum of the series. So here's n equals 0 to infinite, 2 over 5 to the power n plus series summation n equals 0 to infinite, 3 over 5 to the power n. So here again 2 over 5 is less than 1, 3 over 5 is less than 1, so both are geometric series. So then we can find the sum of the geometric series by this formula. So next step, for the first series, first term, what's the first term here? Put n equals to 0, so 2 over 5 to the power 0 is 1. So first term is 1, common ratio is 2/5. So the formula is first term over 1 minus the common ratio plus, similarly for the second series, first term over 1 minus the common ratio, and we simplify, it gives us 25 over 6. That means the given series converges, and in fact converges to this number. Great. Now let's move on. Let's do different types of series here. Example 6. Determine whether the given series, here the series is ln of n square plus 1 over 2n square plus 1 is convergent or divergent. So let's begin the solution. Let's use the zero test. So let's take a limit of the nth term here. So limit n goes to infinite, an equals to limit n goes to infinite of ln n square plus 1 over 2n square plus 1. And this equals to, you can take the natural log outside the limit. The function is continuous, so we can always take the limit inside. That means ln outside, then take limit n goes to infinite of this everything as it is. And then here we can divide by n square to numerator and denominator. That means we have 1 plus 1 over n square over 2 plus 1 over n square. Then take the limit. The second terms on both numerator and denominator, that the fractions form, they goes to 0. Then only left the coefficient of n square over coefficient of n square, which is 1/2. So natural log of 1/2 is not 0 and is not infinite also. Then by zero test, the series diverges. Great. Let's move on. Example 7. Determine whether the given series is convergent or divergent. The given series is 1 over n plus 1 times n plus 2. So let's use telescoping sum idea. So let's write the partial sum. So Sn equals to 1 over k plus 1, k plus 2, and k runs from 1 to n. So I just take partial sum, so I should index here k, by the way. Then using partial fraction technique, the sum is as it is. We can rewrite 1 over k plus 1 times k plus 2 equals to 1 over k plus 1 minus 1 over k plus 2. We can easily verify this one. If you multiply this 1 by k plus 2 and multiply this 1 by k plus 1 and simplify, your k cancels and 2 minus 1 turns out to be 1. So 1 over the LCD of denominator turns out to be this one. So awesome. Next, so let's put the value k equals to 1 here. So this is 1 over 2 minus 1 over 3, which is first term here. Put k equals to 2, so 1 over 3 minus 1 over 4 here, and so on. So the nth term is 1 over n plus 1 minus 1 over n plus 2. Great. Then we can cancel all the terms but except the first and last terms left here, and then take the limit n goes to infinite So when n goes to infinity, this fraction goes to 0. That means we have 1/2. So then the Sn limit is 1/2. That means the given series converges to this number 1/2. So then given series is convergent. Great. Example 8. So this is slightly different type here. Find the value of variable x for which the given series of x plus 2 to the power n, where n equals to 1 to infinite, converges. Okay. Speaking the solution, this looks like a geometric series, and geometric series converges if the common ratio is less than 1. So we start here. So the series is a geometric series with r equals to x plus 2, and we know the geometric series converges if and only if the common ratio is less than 1. Let's solve for x. So this is same as this one. So absolute value of x plus 2 less than 1 is equivalent of saying -1 less than x plus 2 less than 1. Then subtracted 2, so -3 less than x less than -1. So that is the value of x is lies between -3 and -1, excluding the endpoint. Awesome. And in this case, if you want to find the sum, is then due to being geometric series, its sum is a over 1 minus r. So the first term over 1 minus the common ratio. So simplify, this gives us x plus 2 over minus x minus 1. And x lies between -3, -1. Great. So let's move on. Let's do the example 9. This is a fun problem. So that the infinitesimal 0.9999999 is equal to 1. Now we can prove this one. So solutions. So let's rewrite 0.999, which is the given decimal, equals to, we can write down 9 over 10 plus second 9 over 100 plus third 9 over 1000 and so on. So actually this is a geometric series. The next step, this equals to the first term over 1 minus the common ratio. The common ratio is 1 over 10, right? The how to find the common ratio? The ratio of the second term in the first term. So 9 over 10 is square, divided by 9 over 10. That means 9 cancels, 10 cancels, so it left 1 over 10. Then simplify. So here's the next step, 9 over 10 as it is. And in the denominator, so this is 10 goes here, so 10 minus 1, 9 over 10. Awesome. Then it cancels. This equals to 1. Great. So now we know 0.9999 means equal to 1. Awesome. So we end this sections here. Thank you.